Hello. Today we're going to figure out how to get the area of trapezoids, rhombuses, and kites. Those are all the sort of odd-shaped polygons we had, as opposed to rectangles, squares, and triangles. You see those around a lot. Trapezoids, rhombuses, and kites. The names may sound unfamiliar because the shapes themselves are not nearly as common as rectangles, squares, and triangles. Well, triangles are popular because, as we've already shown, a triangle produces a really stable frame, as opposed to a rectangle. You put cross members in, you produce triangles, and you have something stable. So they're very common. On the other hand, squares and rectangles, well, they stack together very well, don't they? It's hard to fit trapezoids together, so they're not nearly as common. And this time, I'm not even going to tell you what the area of a trapezoid is. We're just going to figure it out. Pretend you don't know, which might not be much of a pretense. It's possible that you don't. We have an altitude here for the trapezoid. We have two bases in a trapezoid. Remember, we've got base 1 and base 2, and they are not congruent. And this is not necessarily an isosceles trapezoid. That would be too easy. Well, one of the things we can do right off the bat, this base here, this is B2, so we can write that L1 plus B1 plus L2 equals B2. So we have this relationship, and we're going to find a formula for the area that involves B2, the lower base, B1, the upper base, and the altitude. First thing we do is break up this trapezoid into three parts. The middle here is a rectangle with top and bottom sides equal to B1, and left and right, this is also A over here. They're both the same. There's only one altitude for a trapezoid. Well, that breaks it up into three areas. We've got A1, A2, and A3. This area is the area of a right triangle with altitude A and leg L1. This, of course, is another right triangle with altitude A and leg L2. So we can write those areas out real quick. For our right triangles, they're pretty simple. We've got A times L1 over 2, or 1/2 of A times L1. A times L2 will be the area of this triangle, divided by 2, of course. And what about A2? This is actually A3. A2, well, that's pretty easy. That's just B1 times A. Now, what's all this going to get us? What happens when we add up all these areas? Let's do it. We get A times L1 over 2 plus A times L2 over 2. That's supposed to be an A there, sorry. And this is B1 times A. Suppose I want to pull out an A over 2 from all of these. Well, there is a way I can write this that'll make that happen. Well, I can rewrite this. I can use a distributive law to pull out the A, put that in front, and that's A times L1 plus L2 plus 2B1. Well, where the heck would 2B1 come from? I've only got 1 over here. Well, what I want to do is pull 1/2 out of this whole thing and use my distributive property to put a 1/2 in front of all of it. If I do that, I can put a 2 in front of the B1. In other words, I could just write this as 2 over 2. like that. That's just multiplying by 1, so it has no effect. But when I pull the 1/2 out, it now distributes across all 3 of them, which is what we wanted. So this is just a little trick that makes things work out right. So now we can write a over 2 times L1 plus L2 plus 2B1. But now we just need to rewrite this again. If I rewrite this, just rearrange it a little bit, B1 plus B1 is 2B1, right? But what do I have now? Remember over here? B2, that's this bottom base. That's L1 plus L2 plus B1. And then I have a B1 over here. So I can rewrite this as A over 2 times B2, the lower base, plus the upper base. And that is in fact the formula for a trapezoid. It's the average of B1 and B2 multiplied by the altitude, and then you take half of that. Well, pardon me, you don't take half of that. You take the average of B1 and B2 and multiply it by the altitude. That's where the 1/2 comes in. You're actually taking the average of these two top and bottom bases. You're getting a number. This B1 plus B2 divided by 2 will give you a number that's the average of these two, which would be a little shorter than B2 and a little longer than B1. A times B1 plus B2 all divided by 2. Or I like to think of it as just the average of B1 and B2, which is 1/2 B1 plus B2 multiplied by the altitude. Suppose we have a rhombus. Remember, a rhombus is kind of like a square, except that we don't have 90-degree vertices. It's kind of a squashed over square, but the sides are still all congruent. And remember back from previous chapter, the diagonals of a rhombus are perpendicular and they bisect each other. In other words, each one is a perpendicular bisector of the other. And what that does for us, very similar to the trapezoid, we don't even need a rectangle for this. We're going to break this up into right triangles. Since these are all perpendicular, we got a right triangle here, 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 and here. We've got 4 right triangles. Now for a rhombus, what we have to remember is that the diagonals of a rhombus are perpendicular bisectors of each other. Pardon me, this should be D1 over 2 also. So we've got a ton of symmetry going on here. This is D2 over 2, this is D2 over 2, this is D1 over 2, this is D1 over 2. So we have lots of congruent segments here. These sides are all congruent also. So, for instance, the area of this would be D1 times D2 divided by 2. Here's an altitude and a base. Well, this one over here, D2 times D1. Well, this one over here, D2 times D1. And over here, D2 times D1. All divided by 2, of course. Which means that if I just find one of them and multiply by 4, I've got the area. I think I said multiply by 4. If I said divide, that's not right. You find one and then multiply by 4. If we write it out this way, we've got D1 times D2, and, well, D1 over 2 times D2 over 2 times 1/2. That's the section here, that's one leg of the right triangle, and then the other leg of the right triangle. And, of course, divided by 2. And 4 times that will give us the whole area. Well, what do we have here? 2 times 2 is 4, and we've got a 4 out here. So if we just cancel those, we're going to end up with 1/2 D1 times D2. And that is, in fact, the formula for the area of a rhombus. Notice we're not using the sides to find the area. We're using the diagonals. And now you see the reason. By using the diagonals, we break things up into 4 right triangles, and those we can easily find the areas of. of which we can easily find the areas. Now here we have a kite, and we're going to do the same thing. Let's say this is D1, and this is D2. Once again, the diagonals intersect. It's perpendicular, but they're not bisectors of each other. The long diagonal bisects the shorter diagonal, and that's pretty easy to see because these two sides are congruent, right, in a kite, and these two sides are congruent. So if you just look at this part here, we've got an isosceles triangle. Look at this part here, we've got an isosceles triangle. So when we draw our diagonals, we will split the angle. In other words, bisect the angle, which will cause us to bisect what could be considered the opposite side of this triangle. So that's one easy way to get a kite. You take two isosceles triangles and stick them together. The only catch is the base for each isosceles triangle has to be the same length. That way they fit together. Well, now we've got pretty much what we had before. We've got a right triangle here and a right triangle here. And it's pretty easy to see that they're congruent. This is congruent to itself. These two are congruent to each other. So we've got our HL congruence for our right triangles. And the same thing over here. So if we get this one and this one, we add them up, multiplied by 2, and we'll have these. That is to say, we'll have the whole thing. You can do that now. I've done it for rhombuses, and you saw how we broke things up for trapezoids into a rectangle and a couple of right triangles. Rhombuses we broke up into 4 right triangles. Same thing here. You can just lay it out. This would be D2 over 2, and this will be D2 over 2. This, well, it's different. It's not D1 over 2, but if you label these like L1 and L2, and L1 plus L2 add up to D1, similar to what I did with trapezoids, you'll end up with the same formula we got for the rhombus. 1/2 D1 times D2. In other words, you'll use the same formula for a kite that you use for a rhombus. Just keep in mind that you're using the diagonals, not the sides. This is a little bit different. Most of the time when you're computing areas, you're looking at the sides of things. Well, now we're only looking at diagonals. Well, here it looks like somebody was trying to find the area of a trapezoid. It's tempting to say a couple of politicians tried to do this, but I don't think they'd ever try to do anything as useful as finding the area of a trapezoid. So it must have been one of their assistants. Maybe a clerk was taking a shot at this one. What did they do wrong? Well, let's see here. They've got 1/2 times 14 plus 19. So they've got the average of the base, the two bases, B2 and B1. So this part's right. 1/2 of 14 plus 19. That's cool. Now the altitude, that would be the perpendicular distance from this line to this line. This is a perpendicular line, perpendicular to both of them. So this is the altitude, 12. And wait a minute, they use 13. Well, this isn't the altitude. This is just one side of the trapezoid. You can't just randomly pick sides and decide that they're an altitude. Maybe that's what they were going to do. I guess if they put it to a vote, maybe the majority will decide that this is an altitude. They can vote on it and decide that this is actually right. And from then on, every bridge they build will fall down. But we'll do it the right way. This is an altitude, and it should be 1/2 of 12 times 14 plus 19. And I should point out that since this isn't a science class, I have a bad habit of not always carrying my units through, especially when I know what they're going to come out to be. When you've got a long equation where things are multiplied, divided, added, it's good to carry your units along. That way, when you perform all the arithmetic with the units, if you don't end up with the right units, you know you made a mistake. For instance, I want to have square centimeters when I'm all done here. Well, centimeter plus centimeter is just centimeter, and this is centimeter, so it'll be centimeter times centimeter, which is centimeter squared. This 1/2, it has no units. And so over here I get 6 centimeters and 33 centimeters, which gives me centimeters squared. And this one was pretty simple. Maybe I should have carried the units along with me, but when they're this simple, I don't always do it. But when they're more complicated, it's good to put the units in. And sometimes if you're not sure that you've got the right equation, don't do it with numbers. Just put all the units in. Perform all the arithmetic and see if you get the right units at the end. That's called dimensional analysis. It's got a great, big, complicated sounding name. It's actually dirt simple. And it's a real quick, easy way to make sure that you're using the right equation when things get kind of complicated. In this case, you wouldn't really need it. Now let's see, what went wrong here? Once again, this is way too practical for any congressman to be working on. Who knows who took a shot at this one? They had the right idea. They're using the diagonals to get the area. That's the right thing to do. We don't need it separated. We don't need to know that this is 5 and this is 16. We just need to know the total length of this diagonal. And that would be 21, right? 21 down here, so that's good. But what about this part here? It says 12 centimeters. I believe that 12 is intended to refer to this left half of the diagonal and not the whole diagonal. The whole diagonal here, I'm pretty sure it would have to be 24. It's double this. We know that it's double because the diagonals, the short diagonal of a kite gets bisected by the longer diagonal. Doesn't go both ways, but the short diagonal does get bisected. So the short one is 24. Well, in this case, not so short, is it? This is usually the shortest one. Let's say that the diagonal which connects the two non-congruent sides gets bisected by the diagonal that runs from two congruent sides to the other two congruent sides. In other words, from the vertex formed by two congruent sides to the other vertex formed by two congruent sides. That will bisect the diagonal which goes from the vertex of the two non-congruent sides to the other vertex of two non-congruent sides. That means that he should have put 24 in here. So the right answer would be 1/2 times 24 times 21. Well, we can just divide and call that 12 times 21. Square centimeters, of course, or centimeters squared. So in the end, the correct answer is 252 square centimeters, not this one. Now to work this one out, we just have to remember the formula for the area of a rhombus. They tell us the area is 24 square feet. So we can write down that 24 equals 1/2 of diagonal 1 times diagonal 2. What did they tell us? One diagonal is 3 times as long as the other. That means we can arbitrarily pick one of these and replace it with 3 times the other one. For instance, for D2 I could substitute 3 times D1, or for D1 I could substitute 3 times D2. They didn't tell us which is the larger one. Well, let's make our substitution and see what happens. Maybe we got to go ahead and multiply through by 2 to get all the D1s on one side and constant on the other. So we've got 48 equals D1 times, let's say 3D1. What the heck? D1 squared. Well, what happens if we divide 48 by 3? Well, I think we get that D1 squared is 16. Well, that would imply that D1 equals 4. But if we go back, well, actually we don't have to go back to this, do we? We know that we already decided that D2 was 3 times D4. So if that's D1, then D2 would have to be 12. And what do we got here? 8 and 11, 4 and 12. No, wait a minute. 4 and 12. Yeah, that's one we wanted. Right there. All you had to remember for this one was the formula for the area of a rhombus. After that, simple algebra. Well, this one here, our mission is to find the area of this kite. But they didn't tell us what this diagonal was. We're going to have to find it. But they gave us some other information. This is a right angle. We know that because it's a kite and these are the diagonals. That means we have a hypotenuse of 20 and a leg of 16. So this last length here, let's call it L. We can write that our hypotenuse squared minus the leg squared will equal L squared. That'll give us this length, and then we'll be in business. So if we write all this out, the 20 squared minus 16 squared is L squared. That's 400 minus 256. That gives us 144, which of course is 12 squared, which means that L equals 12. And I was using L for this one section here. So that's 12. Well, remember the diagonal that goes from the vertices joining the congruent sides bisects the other diagonal. That means this is 12. Well, now we got something we can work with, because we got 16 plus 30 times 12 plus 12 divided by 2. Now 16 and 30, what's that? 46 times 24. And we have to multiply that, of course, by 1/2. And if we do that, we get 552. And you could write units squared. They didn't give us any units. But whatever units they were, inches, feet, yards, light years, it doesn't matter. It will be that thing squared will be the area. Although if this was in light years, that'd be one big kite, wouldn't it? This problem is not easy. If you looked at this, figured it out in a couple of minutes, and just sat down and did it right off the bat, I'm impressed. This one actually takes some time. Usually, I'm seeing these problems for the first time, same as you. All you really have to do is take the given information that's given, and one step at a time should lead you to a solution. But some problems are more complicated than others. This one I had to take a look at off the air, so to speak, to make sure I knew what the heck was going on. First thing you're going to do, and you might have spotted this because of the way they drew it, we're going to find the area of this whole thing, the shaded and unshaded sections, and then we're going to subtract out the unshaded parts. Luckily, so you don't have to just founder helplessly trying to figure this out, they give us a hint. In mathematics, it's not good to be proud. If somebody's willing to give you information that'll lead you to a solution more easily or more quickly, take it. Their hint was to draw lines through AC and through D. Actually, you just say, that's not through AC, pardon me, through A and through D, which are parallel to EH. I think that's what they said. And that will help. So the first thing we're going to do, which isn't immediately obvious, but you can see if we drew this line parallel to this line, and these lines are both perpendicular to that line, pardon me, we have, let's see here, from A, and let's call this X. That's what they asked us to do. They suggested it anyway. And their suggestions are always pretty darn good, so let's see here, X. I guess they didn't suggest that, did they? Oh well, I'm going to suggest it. Sometimes my suggestions make sense too. Let's see here. And yeah, we can call this Y. Okay, cool. We've got a point right here where this line intersects this, which the whole thing has a length of 9. The problem is, what's the length from here to here? Well, as I say, over here, because of the way we've drawn these, AE, EF, FX, XA, they form a parallelogram. In fact, in this case, they form a rectangle. But as long as they're a parallelogram, we know that the opposite sides have to be congruent. Well, this is opposite. And they gave us that BF is 16, so that 16 refers to the entire segment. Well, this section of that segment is 10. So maybe I should just write 10 in here to indicate this is the length from here to here. And up here I write 6. The whole thing is 16, and this section here has to be 10 because of, as I say, this forms a parallelogram, so this side has to be exactly the same as this side. Well, we have a right triangle here. Notice we have another right triangle down here. If they were congruent, and if this side corresponded to this side of this triangle, then we would know that this section right here, from this line to C, was 6. And we'd also know what this small little section here was also, because the two of them have to add up to 9. Can we show that these two are congruent? Well, we probably can. Let's see here. This ABCD is a parallelogram, so once again, this side is congruent to this side. Well, okay, we've got two sides congruent. That's good. What about the angles here? Let's say this angle and this angle. Well, we have two parallel lines and then two parallel transversals cutting those lines. That means that corresponding angles have to be congruent. In other words, if we call this alpha here, well, then this would have to be alpha also. This line is parallel to this line. This line is parallel to this line. So they form exactly the same angle right here. Well, at this point, we know everything we need to know. This is the right angle. We know this, and the whole thing adds up to 180. That means we automatically know that this angle, whatever it is, has to be the same as this angle. So for a right triangle, once again, I can point out that the angle and hypotenuse they have hypotenuse and two angles which are congruent, so for a right triangle, that's enough. Well, actually, for any triangle, you've got sine angle side or angle side angle. And a right triangle just makes it super easy because you automatically know one of the angles. That's why a lot of our theorems for congruence for right triangles are in a sense looser than our theorems for regular triangles, because we already know one of the angles in the right triangle. That helps a lot. So we have that ABX is congruent to CDY. Well, that means that since this side is 6, this one here must be 6. Also, this side from here to here, well, this is a rectangle from AXFE. That part's also a rectangle, or a parallelogram, meaning opposite sides have to be congruent. So this is 8. Well, if this is 8, then this is 8. Once again, this right here, DYHG, forms another rectangle. Opposite sides are congruent. If this here, dy, is 8, then this must be 8. Well, now we're getting some stuff to work with here. We figured out how long this is, and this one here must be 3, right? Because the whole thing is 9, so that's easy to fill in. And that means every single one of these must be 3. We have a line parallel to this line. So we could say that this forms a rectangle here, DGHY. So this opposite side has to be 3. Or, also, we could extend it out here and say this forms a rectangle, this section plus FHY. So this has to be congruent to this one. And then, of course, we can say this also is a rectangle from this point to E, H, and Y. So every single one of these short little links here, they're equal to 3. Why do we care? Well, here comes the part that's really strange. In order to get this, now that we have enough, we've filled in enough of our dimensions, what we're going to do is take this part here, AB, FE, and treat that as a trapezoid. Although in this case, I should point out that like B1 and B2 are bases. This trapezoid is on its side. This is the base. Here you can call this B1. And this segment from B to F, you could call that base 2. It's just a trapezoid, but it's laid sideways. It's rotated 90 degrees from the way we're used to looking at them. Well, I went ahead and outlined in yellow the 2 trapezoids of which we're going to find the area. We've got this one here, like I said, ABFE, and then this one over here. Again, this one is tilted over on its side, just like the first one. These are 2 trapezoids side by side, and they're both tilted from the way we're used to looking at them. There's nothing illegitimate about a trapezoid that's oriented this way. It's just that we frequently see them like this, with the bases, with our bases separated vertically. Well, here the bases are just separated horizontally. And we have something else going for us here. It's real easy to compute the altitude of these trapezoids, because one side of each trapezoid is perpendicular to the basis. So when we know the length of that side, boom, we've got the altitude. That helps. So let's do it. What about, remember, it's this BF. It's the right-hand side of this trapezoid. It's the left-hand side of this trapezoid. You could say this is the starboard side for this trapezoid. This is the port BF is the port side for this trapezoid. So what would the area of this trapezoid be? Well, let's see, I think we know that, right? Here is B2, so that's 16, and here's B1, that's 10. So we've got 10 plus 16 times 1/2. If you look at it this way, it's a lot like the area of a rectangle. But instead of using one side, because with a rectangle, two opposite sides are congruent, with a trapezoid, the opposite sides are not congruent. So we take their average. And the cool thing about that is it works. I mean, it's obviously kind of an easy, simple thing to do. But we proved earlier that it's not only simple and easy, it actually works. We take that and multiply it by the altitude, which in this case would be 8. Well, now, if I write this out, we get 8, now that's the altitude, times the average of B1 and B2. That works out to be 104, and I labeled that A sub L1. That's large area 1. That's the whole thing right here. When we subtract, I'm going to call this part, the unshaded part, A sub S for small area 1, and A sub S2 for small area 2. May not be the most brilliant way to label things, but I think it'll work. So we have this large area over here, ABFE. Maybe I should actually write that in so you know what I'm talking about here. A sub L1, that's this one. Whereas A sub L2, that's this one over here. And this is, well, we still have 16. So the side is common to both of them. Plus 9, that's the major side over here. Try to ignore where I've broken up the dimensions because we don't need those yet. What we need is the one that they gave us in the first place, the 9 and the 16. Now this 8 here, we had to get that after we showed that these two triangles here were congruent. Then we knew this side was 8, so this one must be 8. And that's where we got that. That's one of the things that we needed to compute before we did compute this large area here. So this whole thing here is 8 plus 3, or 11, would be the altitude from F to H. And then of course it's 1/2 times 9, right here, 9, plus 16, that's what BF is, that's given, which is 11 over 2 times 25, or 137.5. Now what we're going to do is recognize that we have another trapezoid here. A to D, G to E. And over here we have a trapezoid C, D, G, H. Once again, now we have another DG. DG is one side of each trapezoid. You could say it's like B1 for this trapezoid and B2 for this trapezoid, or vice versa. Now, after I've got the large areas, which I originally put in yellow, outlined them. I think I already showed you this line here. Well, if not, it was, of course, this side plus this side, the average of that times the altitude, which in this case is 3 plus 8, or 11. And we get 137.5, and that's large area number 2, A sub L2. Now we have to compute the two small areas, and I put them in blue. We've got A, D, G, E. I'm going to call that A sub S1, and C, D, G, H. I'll call that A sub S2. If we compute the areas of these two trapezoids and subtract them from the whole area we got, we should be left with the area, the shaded area. Let's see what happens. A sub S1, the altitude is on this side now is 8 plus 3. This is the side that is common to both trapezoids. And it has length 3, just like this one over here. It's 3, 3, 3, and 3 for all of these sections. From the line DY to EH, they all have length 3. So for this one, it's 10 plus 3. We take the average of that. We have the 1/2 10 plus 3, and multiply it by our altitude, which is 8 plus 3. That's 11. So we get 11 over 2 times 13, or 71.5. Down here, same thing. I should have put parentheses here. That's not 8.5, that's 8 times 1/2. The altitude here for our trapezoid now is 8. This is the common side, which has length 3, and this is 9. So we've got the average of 3 and 9 times the altitude. Now we multiply this out, we get 4 times 12, or 48. Now, these two together, in other words, if we add them up, what do we get? Well, now that we've got these separately, basically we've computed 4 different areas. 2 large areas add up to this. That would be the whole thing. Like, well, the A, B, C, H, and E, which is an irregular pentagon. This notation, I just made it up. It's not standard. What I meant to say is you add up A1, A sub L1, and A sub L2, and that's what you'll get. That's the large area. You add up A sub S1 and A sub S2, and you get 119.5. Now, you subtract the small area from the large area. Pretend those two are closer together, and you should get, subtract 119.5 from 241.5, and you get 122. We weren't given any particular units, so this is 122 square units, or units squared. We don't know what units they used. This was not an easy problem. If it took you a while to figure it out, or you didn't figure it out and decided to just watch me do it, that makes sense. Don't feel bad about it. Sometimes making false starts and using up half a notebook full of paper as you make false starts and start over again and then make more mistakes and throw it all away and start over again. You might start feeling like you don't have much aptitude for this. Well, that's not probably true. There's an old saying, if you could see Einstein's trash can, you might not think he was so smart. Even Einstein did things wrong many times before he got it right. All you get to see is the final solution, which is the right one. You don't get to see all the mistakes he made in between trying to figure it out and finally coming up with the right answer. So don't get the impression you're not getting good at this just because it took you a long time to arrive at a good answer. It took Einstein a while too. False starts don't matter. As long as you get to an answer in the end, you're doing fine. Well, that was a super long problem. And that's about it for now.